Hello everyone, let's analyze. So we're going to continue today talking about sequences that converge to a limit. It should make some sense to us intuitively that if a sequence converges, then the limit has to be unique. Let's carefully prove this statement. So the theorem says that if a sequence converges, the limit is unique. So how would we prove something like this? Well, we have two definitions of a limit. If you remember last time, one is a definition, one was a theorem. Of course, we could take the theorem of the definition and then prove the original definition as a theorem. That's what we mean when the definitions are equivalent. So in order to get some exercise understanding the different definitions, what we're going to do is we're actually going to show that the theorem is true using both definitions for good practice. So in the first method, we're going to use that picture to kind of guide our thinking. Of course, it's helpful to have pictures to kind of visualize what's happening. However, it's important that we also not rely on a picture to make a proof for us, since we can't necessarily draw a picture of every possible situation. So it's important that when we write a proof, that the proof we write is independent of the picture, but it is sometimes helpful to organize our thinking using pictures and diagrams. And that's what we're going to do here. Okay, so imagine that L is a limit to our sequence. Okay, well, we know that the theorem definition of the limit says every single neighborhood of L contains all the entries of the sequence except for some finite number. Right? That means outside of a neighborhood of L, any neighborhood of L, there's only a finite number of sequences, entries. That means a neighborhood of M that is distinct from a neighborhood of L can only contain a finite number of entries of the sequence. And if it contains a finite number of entries, well, it doesn't contain an infinite number of entries. Meaning M, any M, cannot be a limit. And that's the proof of method 1. So if you read through method 1, that's essentially what we show. Okay, in method 2, we're going to give an alternate proof. And in this proof, we're going to use the traditional, for any epsilon, there exists n definition, the original definition of a limit. We're going to show if we get arbitrarily close to L, well then we cannot get arbitrarily close to a different M. Or rather, what we're going to show is that if we get arbitrarily close to L and M, then that means L and M are arbitrarily close to each other. And if L and M are arbitrarily close to each other, L and M, L must equal M, or L minus M must equal 0. This is also known as the Archimedean property. The Archimedean property is the property that there exists no smallest positive number or no largest real number, which is a consequence of the complete ordered field axioms that we have. So let's take a look at the second proof. And of course, we don't need two proofs to prove the theorem. One valid proof is sufficient, but we're doing it both ways for practice. So let epsilon be arbitrary. Suppose an converges to L and to K. By the way, the an arrow L, that's a bit of shorthand for saying that the sequence an from n equals 1 to infinity converges and has L as a limit. Since that's a bit of a mouthful, we just use the shorthand that that arrow is usually read converges to or goes to L. If an converges to L and to K, well, we know that there's a natural number n and a natural number n that would guarantee that an minus L is less than half of epsilon for all n bigger than big N, and an minus k is less than half of epsilon for all n bigger than big M. Why can I put epsilon over 2? Well, for any epsilon, I could find an n. So if I can find an n for any epsilon, I can find an n for half of any epsilon. And that's what the big N and the big M is. So let P be the bigger number between big N and big M. Okay. So AP, right, is within epsilon over 2 of K and within epsilon over 2 of L, because P is bigger than or equal to N and greater than or equal to M. So I know that 0 is bounded below by the absolute value, that the absolute value of L minus K is greater than or equal to 0. That's equal to L minus K plus AP minus AP. I just added 0. Using the triangle inequality, this is less than or equal to the difference of L in AP and K in AP, which, because P is the bigger of N or M, we're guaranteed that this is less than epsilon over 2 plus epsilon over 2, which is, of course, epsilon. And epsilon is arbitrary. So we just proved that L minus K in absolute value is greater than or equal to 0 by definition of the absolute value, and is also less than epsilon for any real number. Okay? So it's strictly greater than all negative numbers, because the definition of a negative number is something that's strictly less than 0, and this is greater than or equal to 0. So if the absolute value of L minus K is greater than all negative numbers, it can't be negative. And if it's less than all positive numbers, it can't be positive. Therefore, it has to be 0. Right? That's what the trichotomy axiom says. The trichotomy axiom says a number can't be less than itself, so if it were positive, it would be less than itself. So we know that the difference between L minus K must be 0. So if AN converges to L and AN converges to K, it has to be that L and K are equal. The next theorem says that if a sequence converges, it is necessarily a bounded set. Okay. Now you might notice the subtle difference in how we write a sequence and a set. Okay. A set is a collection of things. A sequence is necessarily an ordered list that has an infinite number of entries, even if the entries repeat. Okay, so there's a subtle difference between a sequence and a set, but of course we can say the entries of a sequence form a set, which is what we're saying here in this highlighted part. And the set is bounded. How do we know the set is bounded? Well, if the sequence converges, it, by definition of what it means to converge, has a limit. And any neighborhood of the limit contains all but a finite number of the sequence entries. So the finite number not contained in a neighborhood of L must have an upper bound, because a finite set must be bounded. The infinite number of entries in L minus 1 and L plus 1 is necessarily bounded, because that those infinite entries are less than L plus 1 and greater than L minus 1. So that means every single entry of AN, the infinite part that's in the neighborhood of L and the finite part outside of a neighborhood of L, both are bounded. Therefore, the entire set of all sequence entries is bounded. Now the theorem is useful because the contrapositive suggests a test for showing when a sequence does not converge. What's the contrapositive? If you recall back to your class on proof techniques, if A implies B, then not B implies not A. In other words, if the existence of A guarantees the existence of B, if B is absent, then A must be also absent, because if it were there, B would be there. So if we apply that principle to this theorem, where we're saying that if the sequence set is unbounded, in other words, we can ascribe no upper bound or no lower bound, then the sequence cannot converge. And if a sequence does not converge, we say it diverges. So for example, let's consider the sequence of partial sums. A1 is 1, A2 is 1 plus 1/2, A3 is 1 plus half plus a third, AN is 1 plus half plus a third plus a fourth up until 1/nth. We typically call this sequence the harmonic series because the limit of this sequence is the infinite sum from n equals 1 to infinity of 1 over n. You're probably familiar already with the fact that that series diverges because the sequence of partial sums diverges. And we're going to show that it diverges by showing that it's unbounded, right? Cannot be bounded. The way we're going to do that is by showing that by looking at a subset of these sequence elements. Okay? We're specifically going to look at A2, A4, A8. In other words, we're going to look at the entries of A corresponding to indices that are powers of 2. Okay, so A to the 2 to the n indice, right? The 2 to the n indice of A is 1 plus half plus a third plus a fourth, all the way to the reciprocal of 2 to the n. Now we can actually group this in groups of powers of 2. What do I mean? Well, we have 1 plus 1 over 2 plus, all right, so that's 1 entry, right, which is 2 to the 0 entries. This is 2 to the 1 entries. This is 2 to the 2 entries, right? The next, if we went from 1/9 to 1/16, right, that would be 2 cubed entries or 8 entries, so forth and so on. Okay. So by arranging them in this way, we can build a lower bound. Well, how is that? Well, let's look at this first grouping, 1/3 plus 1/4. Right? A quarter is less than a third. So if I replace a third with a quarter, I get something less than. An eighth is less than a seventh, which is less than a sixth, which is less than a fifth. If I replace all the entries here with 1/8, again, I get something strictly less than. And I can do that for each of my groupings. So here I have 2 quarters, I have 4 1/8. Here I have 2 to the n minus 1, 1 over 2 to the n's. Okay, so what is this equal to, this lower bound of a to the 2n? Well, 2 quarters is a half, and 4 1/8 is 4/8, right, which is 1/2. And in fact, each term we're going to get 2 to some power of 2 to a power times 1 over 2 to that power plus 1. Right, so the last entry will be 2 to the n minus 1 times 1 over 2 to the n, which is, of course, 1/2. In fact, this is 1/2 and this is 1/2. What we'll get is 1 plus half plus half plus half, and we're going to get n of them. So n halves is half of n. So a to the 2 to the n, right? In other words, the 2 to the n entry of my sequence is bounded below by 1 plus n over 2, and n is arbitrary. Okay. Because n is arbitrary, half of n plus 1 can be made arbitrarily large. That means for any arbitrarily large number, I can find an entry in my sequence bigger than it. Because for any number I can find an entry of my sequence bigger than it, that means I cannot possibly find an upper bound. And if there is no upper bound, the set is unbounded. And if the set is unbounded, the contrapositive of our previous theorem says this sequence cannot converge. So it diverges. That's all for today. See you next time.